Okay, we're doing exercise 11C from the first year mechanics textbook, and we're looking at question 3. Okay, so I've got velocity as a function of time, and the first thing I'm asked to do is to sketch a velocity time graph. So let's look back at the function. So that's a quartic. Yeah, I've got t squared, and then that's also going to have a t squared. So you do know from your core maths what a quartic graph looks like. So this is one they could expect us to sketch. Obviously, if you've got a graphical calculator, makes this question a heck of a lot easier. So if you don't, that's absolutely fine. So if you remember sort of the general shape of a positive quartic is a sort of W shape like that. And don't be tempted to start expanding this out, because if ever you want to sketch a graph, you want it factorized, and that is fully factorized. So in fact, we've got 2 repeated roots. So we've got, sorry, it's not y, is it? It's b. So we've got t squared and 6 minus t all squared. So we've got repeated roots at t is 0 and t is 6. So if I was to sketch the whole graph, it would be looking something like that. That's gone a little bit away from 0, but imagine that's at 0. And also the y-intercept is 0, isn't it? If you were to expand that out, you wouldn't have a constant term, so y would be 0. If I go back to the question, this function is only valid for values of t between 0 and 6. So my graph, see if I can log this out accurately, should only start at t is 0 and end at t is 6. But you do need to include, so it's velocity and time. But so you do need to make sure, though, it's sort of, I might even just, let's just sketch that whole thing again a bit neater. Because I'm trying to get to is, you do need to make sure at the 0 and at the 6, it does look like it's flattening out to a stationary point. Okay, so velocity and time. Okay, not the neatest in the world, but that's all the key points. And then find the maximum value of v and the time at which it occurs. Okay, so maximums and minimums, we're thinking about differentiating. And if I'm going to differentiate, I do want it all expanded out. So, v equals t squared. So if I square out the 6 minus t, and then multiply all that out, so I get 36 t squared minus 12t cubed plus t to the power of 4. So if I differentiate that, okay, I'm after a stationary point, so I'm after when that is 0, so I can, so I can take t, in fact I can take 40 out as a common factor, so I can cancel through by the 4 completely. So let's just do that in 2 stages. So I cancel through by 4, I get that. And I already know where 2 of my stationary points are, so I know I've got a stationary point at 0 and 6. So I'm going to cancel through by 4. So then if I take out a common factor of t, and I'm also just going to switch the order a little bit, ready to factorise. So I can take out a common factor of t, and then I can factorise that quadratic. And there's my 3 stationary points. Okay, now you might notice something about that, and in fact some of you might have already sussed this, particularly if you had a neat sketch on your graphical calculator, or if you can remember your quartics, that is going to be symmetrical. So that does make perfect sense that t is 3. And if you were completely confident about that, you could have just used t as 3. It does make sense that it's the midpoint between 0 and 6. Okay, So what are we actually trying to do? We're trying to find the maximum value of v and the time at which it occurs. Okay, well that's fine. So we've got the time at which it occurs. We've kind of answered this a little bit back to front. So it occurs when t is 3. It's that point there. So when t is 3, v, so I'm just going to look back to here. So v is 3 squared times 6 minus 3 squared. So 9, I make that 9 times 9. So I'm going to double check that. I make that 81 meters per second. Lovely.